Last week, we talked about rational numbers, and today we're going to talk about the difference between irrational and rational numbers. So that's our essential question. How is an irrational number different from a rational number? So what, first of all, is a rational number? A rational number can be written as a fraction. Thank you. All right. So a rational number can be written as a fraction. So think about it. An irrational number cannot be what? Can't be a whole number, but if a rational number can be written as a fraction, an irrational number cannot be
a fraction
written as a fraction. Okay? So irrational numbers are going to be decimals, only decimals, and they cannot repeat, and they cannot end. Page 15 in your book is where we're at. Page 15. Thank you. So, irrational numbers will end up being decimals that do not repeat and do not terminate or do not end. All right, so that's where we're headed. And by the end, I can identify a number that is irrational. That's what our goal is for today. Here we go. Sophia wrote a decimal as a fraction. Her classmate Nora says that her method and answer are not correct. Sophia disagrees and says that this is the method she learned. So look at the little example down there at the bottom. Is Nora or Sophia correct? And explain why you think one of them is correct. Well, Sophia did the work. This is Sophia's work. She thinks it's correct. Nora is saying, I think you made a mistake.
Which one, Sophia?
I don't care. Sophia did the work on the paper. And we're judging whether or not her work is correct or incorrect. Any thoughts?
I think it is not.
Why do you think it's not correct?
Yeah, she did not simplify it.
She did not simplify. Okay, so 12 over 99 is a fraction that can be simplified. So that would be at least something to say about her work. But is the fraction value correct to represent the decimal?
It's correct. She could have.
Okay, look real close at the decimal.
Wait,
Elliot?
did I move it?
It says like 1, 2, 1, 1, 2.
Okay, so is this a repeating decimal?
Yeah.
No.
Ooh, I heard yes and I heard no.
It's not.
Is the value that she uses for x the same as the value of the decimal?
No.
Okay, so even if we did something like this, where we put the repeating bar over that 12, whoops, got it. Thank you. I don't know why it tells me that every time. Okay, so even if we put the repeating decimal over that, oh, okay, that's interesting. All right, over that, that's not the same as the decimal that we have written out here. 1, 2, 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, 1, 2. Okay, that's a different value. And so Sophia, the math that she did is good math. She just did it for the wrong number. Does that make sense? Okay, so she didn't see what the number actually was. So there is a problem with Nora's work, with Sophia's work. Unfortunately, Sophia made a mistake. All right, so let's see. I just realized a minute ago that when I write on my whiteboard up here, it doesn't show up on my computer screen, which means it's not that's not part of the recording. I'll have to think about that. But I'm going to keep recording as it is. Okay, so we are going to look. Whoops! Whoa! What was that? All right, there we go. Focus on math practices. So then the question becomes down here at the bottom: is the number that they give us, that 1, 2, 1, 1, 2, 1, 1, 1, 2, and so on, is that a rational number? What did we? Okay, so how did we define an irrational number? It's a decimal that does not
Have a
repeat or terminate. And we know that this one does not terminate because the ... tells us it keeps going. and it does not repeat, even though there's a pattern. Is there a predictable pattern with this number? Yeah, there's a predictable pattern, but it's not a repeating pattern. It doesn't do the same thing over and over again, okay? So a pattern is different than repeating. And so even though there's a pattern, it doesn't repeat, so we can't write that one as a fraction. All right. Whoops, I missed a slide. Got to go back one. Okay, so this one, if we answer this question B here, what is another non-terminating decimal number that cannot be written as a fraction? Do you know of any non-terminating, non-repeating decimals?
98.
That's not even a decimal. 98 is not a decimal, so. There's a famous one that we use in some formulas and stuff. Starts with P, ends with I. Pi, there you go. So pi is an irrational number. It's a decimal that never repeats and never ends, okay? And so we do know some irrational numbers, and we even use some irrational numbers in the math that we do. Hey, a video, what? So I'm going to push play on the video. Let's see what happens. Well, look at that, it's playing.
It's a live video.
How is an irrational number different from a rational number? Think about this question during the lesson. The Venn diagram shows the relationships among rational numbers. A number that can be expressed as an integer or a ratio of two integers is a rational number. When expressed as a decimal, the decimal is either terminating or repeating. An integer is a positive or negative whole number or zero. Whole numbers are the positive integers and zero. Whole numbers have no fractional or decimal parts, and they do not include negative numbers. A natural number is a positive integer greater than zero. Negative numbers and fractions are not natural numbers. How would you classify the number 0.247583326 and so on? How can you use the definition of each number set to classify numbers? Is it a natural number? No. Decimals aren't natural numbers. The same is true of whole numbers and integers in general. Then maybe it is a rational number. Is the decimal a terminating decimal? How do you know?
Okay, so these sets of numbers, this little diagram, it's a box within a box within a box, right? So all the numbers on the screen right here, in this part of the screen, are rational numbers. All of them are. But then we kind of move over to the next box, and now we've got some integers, and they are integers and they are rational numbers. Those two are all rational numbers. Not all rational numbers are integers, but all integers are rational numbers, right? And then you've got whole numbers and you've got natural numbers. Natural numbers think of those as the numbers that you count with. If I can ask how many students are in this room, or how many blue cars are in the parking lot, or how many Oreos did you eat at the party, those are all numbers you can count. 1, 2, 3, 4, 5, 6, 7, right? And then whole numbers, this is really weird. Whole numbers, all the same natural numbers, except for one. There's one different number, and that's the number 0. Because I can't count 0. How many Oreos did I eat yesterday? 0. I can't count that because there weren't any there, right? So that's it. 0 is a whole number, but it's not a natural number. And then we have the integers. Integers are all of those natural numbers plus 0, and then all of the opposite signed natural numbers. So negative whole numbers, negative 1, 2, 3, 4, 5. Already? Okay, so negatives, negative whole numbers. And then rational numbers, what we've been talking about, all numbers that can be written as fractions. So it includes all the whole numbers, and then it includes all the fractions and decimals that we can make that are rational, okay? So that's that. Now we're going to talk about this guy. It's not any one of those, and so where do we put it?
The number is not a terminating decimal. The 3 dots at the end tell us that the decimal goes on forever. We don't know what they are, maybe 5, 8, 3, but we do know that they are not repeating, nor are they all 0. So is the given number a rational number? It can't be. The decimal is neither terminating nor repeating. Numbers that are not rational are called irrational. An irrational number is a number that cannot be written in the form a divided by b, where a and b are integers and b is not 0. The number 0.2475836 and so on is irrational because the decimal expansion is non-repeating and non-terminating. Irrational numbers include non-repeating decimals, most positive and negative square roots and other roots, and special numbers such as pi.
Okay. Yeah, let's keep going.
Suppose the decimal was written as 0.2475836. Would this decimal be a rational number?
If we took away the dot,
Yes.
is it now a rational number?
Yes.
Yes, it is, because now it terminates, it ends. And since it has an end, we can write that as a fraction.
Now the decimal terminates, so it would be a rational number. It's 24,758,326 1000 millions. Now you know how the different types of numbers are related and how to classify them.
He said that weird. Ones, tens, hundreds, thousands, millions, billion, millions, 10 millions, 100 millions, billions. So I would have said it 24,758,324 billions. Or 100, I lost track. Anyway, he said 10 millions, that's weird. 10 million, that's 1,000 million, which is a billion. That's weird. I don't know why he says it that way. All right. Guys, this all looks very confusing. Don't get hung up on it. Anytime we're gonna talk about these, you always have that picture in your book, and just think about where the number goes. Which one of these does it fit in, right? So that's kind of what they're gonna do I think this is like in the middle of your page 17. And it's already got it filled out, I think, doesn't it, where you can see where these things go. So where does pi go? Is it rational or irrational?
Irrational.
Irrational. Pi is irrational. So pi goes to this one. Where does 3.565565556?
I don't like that.
That one is also irrational. That one would go there. What about 0.04053661 ... Also irrational. That would go there. Then what about negative 17?
Rational.
That's rational. What about, I don't know why this repeating bar extends like it does like that. 0.76 repeating. Since it repeats, it would go here, rational. And this one, 3.275, it terminates. And since it terminates, it's rational. Okay? So we need to be able to differentiate between numbers that are rational and numbers that are irrational. We need to be able to figure out which one it is. All right, so. Okay, let's talk about square roots. How many of you ever talked about square roots before? Danica, you've talked about those?
Yeah,
Yep.
Minneapolis, but I don't remember.
Okay, that's fine, and we're gonna go through them again. So it's just as long as you understand what the symbols mean and all that. So we're gonna classify the square root of 3. Is the square root of 3 rational or irrational? Well, let's talk about it. And this is one of those weird mathy kind of things where they call it the non-negative square root. If something is non-negative, what is it?
Positive.
Positive. I don't know why they don't just call it positive. That's kind of weird to me.
I
But
love how they try to confuse you.
right, sometimes I really feel like they're trying to be so technical with their language that it's just unnecessarily confusing. Because I would have just said positive. It's the positive square root of 3. So the square root of a number is a number that when multiplied by itself equals the original number. So they give us these examples down here. Oh, by the way, this symbol is called a radical symbol. So sometimes square roots are called radicals, okay? And it's just a term, it's a math term. The word radical gets used in other contexts as well, like, somebody that's a fanatic or something is called a radical sometimes. That has nothing to do with this. This is just a word that they use in math to describe that symbol. So a radical is the symbol. So if we click on this one here, this shows us that 1 times 1 equals 1. And that shows us then that when we do that backwards, the square root of 1 is 1. So that's the numbers that are multiplied by themselves to get that square number. So this square number is 4, and we get that by doing 2 times 2. 2 times 2 is 4. And then if we work that backwards, the square root of 4 is 2. Okay? And then here, think about this square number, if I take 3 times 3, that's 3 squared, right? 3 squared is 9. And so if I do that backwards, the square root of 9 is 3. And so you guys know about, squaring numbers. Like if I do this, 5 squared, what is that?
That's 5 times.
It's 5 times 5, right? Which is 25. And then if I do that backwards, that would be the square root of 25 is 5, right? Because it would be 5 times 5 to get 25. And so a square root is just the opposite of squaring a number. It's working that backwards. And so we have numbers that are perfect squares. That means I can do this real simply, like 25 is a perfect square. So we had 1 is a perfect square, and 4 is a perfect square, and 9 is a perfect square. What would be the next perfect square after 9? 16. Yeah, this one was 3 times 3. So then we would do 4 times 4 to get 16. Then the next one is 25. 5 times, what's the next one?
36.
36. 6 times 6. What's the next one?
7 times 7.
7 times 7 is 49. So you can see it's easy to find perfect square numbers, right? You just take a number and square it, and then you've got a perfect square. So now, think about this. Are there more perfect square numbers, or are there more not perfect square numbers? Yeah, because look at how many, if we do from 4 to 9, there's numbers in between there that are not perfect squares, right? And then from 9 to 16, there's a bunch of numbers that are not perfect squares. And then from 16 to 25, there's a bunch more numbers. So every time we get those perfect squares, they get bigger and bigger, but there's more and more numbers between them, right? So these numbers, the square root of a perfect square, are rational numbers. Square root of 25 is 5. That's a rational number, yes? What about the square root of a non-perfect square? What about the square root of 3? Was our square root of 3, was that wasn't on here. That wasn't a perfect square. So you know what that number is? If this one's rational, what am I going to tell you that one is? Square roots of non-perfect squares are irrational, always. Okay, there's no exception. So all square roots of non-perfect squares are irrational. So if this number under the radical isn't a perfect square, then that number becomes irrational. Okay? So, we good with that? So here, oops, I gotta turn this off, sorry, clear. This one, okay, there we go. So, and this kind of goes through some of that same stuff I just said. The number 3 is not a perfect square. So the square root of 3 cannot be written as an integer, and then therefore, square root of 3 is irrational. All right, what's next? Or was this page 17 that we're on, middle of page 17?
Yeah.
Okay, middle of page 17. Classify each number as rational or irrational and explain how you classified it. I think it's already filled out in your book. So where is negative 81,572?
Rational.
It's rational. Okay, what about square root of 11?
Irrational.
That's irrational. What about 56366?
Irrational.
Okay. Irrational, that does not repeat, does not terminate. And then square root of 16? Rational, because that is a perfect square, right? 16? What is the square root of 16? 4. There you go. All right. So, and then this slide, just this is again, you have this is what you got in your book, so it explains all those reasons why those numbers are in the place they're in. Let's talk about these. This is down at the bottom of page 17. So, can you classify each number as rational or irrational and then explain it? So, rational or irrational and explain it. Okay? Oh, if I use this tool, that shows up on the screen, then it's on the video. Cool. I didn't think of that. All right, yeah. Okay, so I've been using the wrong tool to write with. Sorry, video watchers. All right, classify each number as rational or irrational and explain why. So 2/3. Rational or irrational?
Irrational.
Why rational?
Oh, because it's a fraction.
Because it's a fraction. It's already a fraction. It's a, yeah, so it's got to be rational. What about square root of 25? Rational, because it's a perfect square. I like it. Okay. What about negative 0.75 repeating? It's rational because it repeats. Somebody said it. Okay. What about square root of 2? Irrational because it's not a perfect square. Okay, then 7,548,123. It's rational because I could write that as a fraction. I should have left a little more. If I put it over 1, now it's a fraction. I've written it as a fraction. It's rational. Okay? All right. Good. Okay, I think next, now that's the wrap-up screen. So your assignment is pages 18 and 19?
Darn it.
Nope, 19 and 20. My bad, 19 and 20. So your assignment is not this page, it's 19 and 20. So start here. So, what? This thing's in my way. Okay, pages. Oh, I can't write over there. Maybe I can't write over here either. You see me writing, don't you?
Yeah.
Now it'll do it. What in the world?
Maybe you weren't writing.
Now I'm erasing and it won't erase either. It's like there's a dead spot or something over here. So,
Mr. Brown Boy has that.
there we go. Pages 19 and 20. That's our assignment. When's it due?
Tomorrow.
Tomorrow. Tomorrow? How much time do you spend on homework at home?
30 minutes.
30 minutes
Or
is the
more.
max on homework at home, okay? And then if you don't get done, bring it in. We'll take questions tomorrow to start class.
If it's late, do you lose points for that?
Yes.
Does that make kids want to work on it longer?
But you have tomorrow in class to ask questions on it and finish
Oh,
it during
it's
that
due
question
after
time.
class.
Yeah,
I thought it
it's
was
due
due
at
during
class
class.
time.
Okay.
So, but if we're working on it together at the beginning of class and I take questions on it and you
Don't
get
write
those
it down,
done.
then you're like out of here. You're like
All right.
not gonna